Good morning everyone. This is the video presentation of our Solitude project, Safety Arguments for Learning-Enabled Autonomous Underwater Vehicles. In this project, we are interested in autonomous missions conducted by underwater vehicles, especially for the deep reinforcement learning end-to-end control techniques. The left figure shows a deep reinforcement learning framework of our docking mission. The underwater robot observes the current state from the marine environment. The actor neural network makes decisions based on the current states, and finally, the underwater robot executes the decision results and interacts with the marine environment. To verify the reliability of this system, we decompose it into two cases, white box and black box. In the first phase of the project, we conducted a reliability analysis of the image recognition network, i.e. CNN neural network of the underwater robot. In the second phase, we validated reinforcement learning modules. If we want to verify a DRL algorithm, it is natural to verify the according environment since DRL need to interact with the environment, which is different from CNN verification. However, the environment is hard to model. Sometimes there is no environment model. This kind of challenge motivated our research. Here, we first consider the white box deep reinforcement learning, which means we can obtain the information of neural networks and environments. For example, we could calculate the action decision for a given observation. Furthermore, for a given state and action, we could predict information of the next state. In terms of this kind of application, we say they are white box deep reinforcement learning algorithms, and then we can do safety verification based on the reachability algorithms. In this project, we use a reachability verification tool to verify the safety of DRL in UUV applications. To verify a given DRL system and calculate the probability of crash per random initial condition, PCI, we need the following information. The details of DRL actor neural networks include the number of layers, number of neurons, neural network weights and bias, activation functions, and so on. We also need the model of environment and robot, such as the kinetic model and transition probability. Here, we will show you the basic idea of our reachability verification procedure. First of all, we have a real environment and a real underwater vehicle. The UUV is running in a marine environment to arrive at its docking cage. To employ our verification tool, we construct an equivalent environment model. At the same time, the UUV observes the environment and gets the initial state variables. We notice that the real environment might have disturbance, and there is a gap between the real environment and the equivalent model. However, these differences are modeled and reflected in an uncontrollable error signal epsilon to the real UUV position. Therefore, we can build the initial state range that covers all possible real positions in terms of the according disturbance levels at an initial state. Then, based on the state range and a given actor neural networks, we use our verification tools to calculate the over-approximated action range. Next, we can obtain the over-approximated next state range based on the current action range and current state range. Until now, our reachability verification can be operated as a loop. So far, we have a complete verification framework. Each step is an over-approximated estimation, which guarantees the conservativeness of the proposed algorithm. As shown in the figure on the right hand, our algorithm can guarantee that the UUV must appear within this yellow range at any time. If the yellow region does not overlap with the unsafe area, then we say the initial cell is safe. The animation on the left shows the approximated operational profile projected into a 2D space as more and more operational data, i.e., the trajectories of the deep reinforcement learning algorithm, is collected from the statistical testing. In this project, we divide the initial space into several small cells. Theoretically speaking, when we finish the verification of all cells, we can accurately estimate the model's safety in the whole initial space. However, due to the limitation of computing power and the scalability problem, we use the sampling method to estimate the safety of the entire input space. Here is the illustration of our verification tool in an initial cell. Due to the existence of disturbance, we summarize all possible subcases in the left figure. The UUV will be safe in case A because the real and observable paths are safe. In cases B, C, and D, the UUV is unsafe since at least one signal shows that the crash occurs. If the sensor misdetects the distance perception in a corner case, the decision of the current policy will roughly crash the vehicle with high probability. Consequently, these errors should also be considered in safety verification problems. Based on the reachability verification tools, we could use an interval to bound the real paths around the observable path. The right side figure shows that all the real paths will be bounded in green intervals. The 6 figures here illustrate the verification results of an initial cell. The green stripes are the reachable set of state variables. For each time slot, the real state variables can reach any position in the green stripes. In our UUV application, we have 6 state variables, which are 3 position variables and 3 rotation variables between UUV and the target. We can see that the state variables 1, 2, 3 and 6 are converging to 0, which means that the UUV will finally align with the destination and finish the docking mission. Here, we notice that state variables 3, roll rate and 4, pitch rate are not changed because DRL algorithms cannot control them. Therefore, they will not change under ideal conditions. As aforementioned, for every single cell, we can conservatively estimate the safety of the DRL policy. The initial cell is unsafe if the reachable set overlapped with the unsafe area and vice versa. After we have the operational profile and the safety performance of each cell, we can calculate the overall reliability of the given DRL policy. The reliability metric PCI is then the sum of products on both types of estimates at the cell-wise level. The plot on the right hand shows the reliability claims stated in PCI. We may observe the result starts to stabilize and converge as more and more statistical data is collected. Such PCI claim forms the top claim in our safety arguments for lower-level deep reinforcement learning components. We notice that the reliability of the DRL policy is not very high. The main possible reasons are in 2 points. First, the safety issues are not considered and modeled during DRL training. Second, the verification tool is an over-approximation method, generating more conservative results. In this project, we use the BlueRov-2 unmanned underwater vehicle as our real-world application. The mission is to safe dock into that cage. For illustration purposes, we build the models in ROS and gazebo simulation. As shown in the left figure, we will randomly reset the initial position of the BlueRov-2 robot in the water tank, and the robot will be controlled with an actor neural network, which is trained by the deep reinforcement learning algorithm. In the visualization software RVIZ, we use a dark blue cube to represent the docking cage, while a dark green cube represents the reachable areas that the robot can reach every moment. The black mesh grid represents the marine environment. In the beginning, the reachable position of the UUV is going to be larger and wider. We can see here, the reachable range of the UUV is bigger than the docking cage. However, under the control of the verified DRL policy, the reachable range of the UUV gradually shrinks. Now, the reachable range of the UUV will be completely wrapped within the cage frame when approaching the destination. Here, UUV may appear in any of these reachable positions. There is at least one position that is not terminated in the reachable set, and therefore we need to continue to verify whether the UUV will collide within the cage. After the verification, the UUV will safely search for destiny in the cage, as shown in the animation here. Therefore, we think that the UUV will arrive at the destination 100% safely from these starting points. Here are more case demos without a crash. Here are some case demos with a crash. As the number of steps increases, the area reachable by UUV is constantly changing. Here, we found that the reachable set expands dramatically, which is because the policy outputs at these initial cells are not stable. For example, if the action range is 0.5 meters per second in the x-axis, then the reachable range of UUV would be 0 to 0.5 meters in the x direction. Here, we see the reachable set is colliding with the docking cage, which may cause some unsafe consequences. More specifically, if the robot is always taking the maximum action from the initial state, then the UUV may crash now. So we divide such initial cells into unsafe cases. However, since our verification algorithm is an over-approximated method, UUV may appear anywhere within the reachable set. Therefore, even if the reachable set collides with the docking frame, the UUV may run in a safe position within the reachable set. Now, we can see that our DRL policy will eventually control UUV to its destination if the UUV does not crash. Here are more case demos with a crash. After considering the white box verification of DRL, we now consider the black box scenario, where the details of the robot's policy and environment are unknown. We only can query the information from the environment, but we cannot model it. For this black box scenario, we designed a potential training loop for DRL algorithm to get safer results, as shown in the right figure. The DRL policy can be obtained by the training process. After that, we do some abstraction to build a DTMC failure model, which is shown on the right. After we check the different properties of the DTMC model, we can have assessment results of the current policy. Finally, we can retrain the model if the assessment results are not acceptable. To evaluate the performance of the DRL models in an agnostic environment, we define several safety properties. Safety, robustness, resilience, detection and recovery. Safety is to check the agent can still work or not. Robustness expresses the ability to complete the mission regardless of the disturbance. Resilience evaluates the accumulated deviation from a negligible risk trajectory. Detection concerns how fast the robot's risky situation may deteriorate, and therefore be detected. Moreover, recovery concerns how soon the robot can recover from a risky situation. The properties are defined in a quantitative way with PCTL, the probabilistic computational tree logic. Thank you for your attention. Please refer to our Solitude project website for more technical details, source code, deep reinforcement learning models, datasets and publications.